Welcome back to the third session of Basic Mathematical Intuition for Robotics. We're about to start the third session, which is trajectory planning, and we already finished the first two sessions, which happened the day before yesterday and yesterday. We have two more sessions remaining in this course, which will be live streamed tomorrow and the day after. Before we start off, I'd like to thank all of you who have watched the first two sessions and all of you who have joined in for this third session as well. Right now we have 6 people who have joined in, and there are more continuously joining into this live stream. Though we do post all of these videos after the live, it is highly recommended that if you do want to take this course, take them during the live sessions. You can ask questions, and live sessions are always much better. Okay, so we have a few people who have joined into this live stream for the third session of Basic Mathematical Intuition for Robotics. And so I guess we will get into the session without any further ado. So before we start off, we'd like to go through a quick recap of whatever happened in the previous session. It's going to be a very quick recap. And what we learned in the last session was about kinematics. So we realized that we could use DH parameters, of course not the only way, but one of the methods of creating a transformation matrix was the DH parameters, where we could have one matrix that could relate the end effector's frame to the base frame. So we would have world coordinates and we could figure out exactly where the end effector is. So with this one transformation matrix that we created using the DH parameters, we could actually relate all of the angles and lengths of our joints, which we call the joint variables, with the position of the end effector in three-dimensional space. So this relation is what we call kinematics. Forward kinematics was where we used the angles of the different joints and the position of the different joints, which is for a revolute and prismatic joint respectively. And using those, we found out where the end effector frame is. We found out where our tool connected to the robot is. Inverse kinematics was where we knew where we had to go with the end effector, and using that, we reverse calculated to find out what the values of the angles and the other joint variables should be. Just to note, forward kinematics is much easier to compute than inverse kinematics, and inverse kinematics is nonlinear. It has sine and other trigonometric terms, so there can be multiple solutions and singularities and things like that. We will talk more about those in the next course altogether. This session, today's session, is about trajectories. So trajectories is what we're going to be doing in this session, and it is the actual path taken by the end effector, including constraints such as path, velocity, acceleration, etc. So when we have this particular robot, we already saw in the last class that we could get from one point in 3D space to another point in 3D space just by changing these joint variables. But the problem with changing joint variables is that we don't really know what the actual path being followed by the robot is. And there might be an obstacle and stuff like that. So we have to decide something called a trajectory, which decides the actual path in which our robot will move. And it's not just about this path. We also have to consider velocity and acceleration and things like that. Because at the end of the day, our robot is just using motors and things like that, which do have constraints. They have a maximum velocity, they have a maximum acceleration. And also in our next session, session 4, we will talk about how we have to maintain the total angular velocity and the total torque, because that can actually cause our robot to topple over. If we have a too sudden movement, our robot will fall over. So we have to decide what the velocity, what the acceleration, and all of that is in the course of our path from A to B. Trajectories are hence of two types. Our first type of trajectory is called point-to-point trajectory. Point-to-point trajectory is where we want to go from point A to point B, and we might know that, okay, there is something in between, so we can't directly go from point A to point B. So all we do is define a third point called point C, or doesn't have to be only a third point. We could have multiple intermediate points, and the main aim is that the robot is going to go from one point to the other, and hopefully with just that much it's going to avoid the obstacle. The other type of trajectory is called continuous path trajectory. Continuous path trajectory is where we do care about every single point in the path. It's a continuous path and we have to go through every single point. Why we would need this is for robots such that do painting, parallel drawing, or maybe welding. Point-to-point trajectories are generally used by robots that are pick and place. So they just want to pick up an object from one position and place it in the other, and the path that it follows really doesn't make too much of a difference to the actual use of the robot. On the other hand, continuous robots, the continuous path trajectory robots, the path really does matter. If you are welding something and you have to weld from point A to point B in a straight line, you have to make sure that you're going in a straight line and you cannot go in any other way. So an example of a point-to-point trajectory would be this that we have right here. We have to go from point A to point C via a point B. So we call all of these intermediate points as via points, and we generally say that, okay, if our robot reaches through this via point, we will be able to avoid an obstacle. So for example, if there was an obstacle right here, we know that if we were going just from A to C, we probably would have hit the obstacle if it was, for example, a 2R planar robot. But just by adding in this point B over here, we can actually avoid hitting the obstacle over here. And the thing is that being a point-to-point trajectory, as you'll see in the next few slides, we don't necessarily have to reach B. We can kind of miss B by a little bit, because we just have to know that we have to go close to B to avoid the obstacle over here, and that should be enough. Whereas continuous path trajectories are totally different. They have to go exactly according to the path there is to follow, and they have to touch every single point. Now, the thing is, why we would prefer a point-to-point trajectory rather than a continuous trajectory when continuous is not required is because point-to-point, we could compute the inverse kinematics only for point A, B, and C. Whereas continuous, we'd have to compute the inverse kinematics for every single point at a given time frame. Every single point we have to calculate the inverse kinematics, and that would cause a huge amount of computations, and that would really slow down your robot. So unless it's really required to have a continuous path defined, we generally don't go by continuous path trajectories. We use point to point, and we do certain mathematical operations to figure out the rest of the path between these points. And that's why this entire trajectory planning for this course, we will be talking about point to point. Now, the next thing that we really need to understand before we get into the math is what is joint space versus task space. Your task space is where the actual task of the robot is going to be performed. So it is the 3D world. It is going to be defined in terms of X, Y, and Z coordinates. And your user, suppose you have a pick and place robot, your robot can only decide, okay, this particular object is in coordinates 3, 5, 6. And that's what the world coordinates are. And that is called your task space. On the other hand, joint space is your joint variables. It is theta and L or D. Your values of each of the joint. What is the angle within which this joint is? What is the distance? And this has to be there for every single one of your joints. So you'll have theta 1, theta 2, theta 3, etc., etc., L1, L2, L3 for each of your prismatic joints. Your thetas you have for your revolute joints. So there are advantages and disadvantages of using your task space and joint space. But the main thing is that your task space is easily defined by the user, and you can actually visualize your trajectory if you give it a joint space trajectory. If you give it a task space trajectory and you say that, okay, we have to move from point A to point B in a circular path or some other path, we can actually state it and we can equate what the equation of this path would be, and we can find out all of the X, Y, and Z values to do that path. But the disadvantage, as we said, is that it's very computationally exhausting. And also we might have kinematic inconsistencies, which means our robot has specific joints, and there are chances that, okay, we say that we want to follow this particular straight path from A to B, but the way our robot has joints, it won't be able to reach that position, and it will be literally impossible. And I will show you one certain case of this, but yeah, that is a disadvantage of defining trajectories in the task space. Joint space, on the other hand, it's much faster to compute. Our robot can determine all of this in real time because we're going to the joint space is what the robot is actually going to be implementing. It does not have to do inverse kinematics once your joint space has been defined. That means your joint space, we're talking about all of the thetas and the L. So we are talking about how the value of theta or the value of L is going to change with respect to time. So we're going to say that, okay, the angle is going to be 30 degrees, 45 degrees, then 60 degrees after another 10 seconds. That is joint space. That is why it's much lesser computations, because inverse kinematics is not having to be applied. But to find out what your joint space trajectory should be, you will have to apply inverse kinematics. But the thing is, the number of times you have to apply inverse kinematics is much lesser compared to if you were to do the entire thing in the task space. And your disadvantages of joint space is that we cannot really visualize the trajectory without actually simulating it, or it's much harder to visualize. Some people would be able to visualize, but it would be much harder. Point-to-point trajectory planning is the first thing that we have to do. Point-to-point trajectory planning is from point... Okay, before we get into point-to-point trajectory planning, let's actually take up an example of this, right? So over here, we have a 2R robot. This 2R robot has two revolute joints. And let's say that this is point A, this is a via point B, and this is point C. And for our example over here, we're going to do a theta value. So we want to find out the joint space trajectory of theta. So we want to see how theta is going to vary with respect to time. And this is the task space trajectory that we have to follow. This is the actual trajectory that we have to follow. And we're going to define theta only for this particular link. Of course, we could have a theta for this link as well, and we would need it while actually programming. But for the sake of this course, we're going to, and of course, because we don't have much time, we're going to deal with theta of this particular link only. So we are looking at this theta from this frame to this frame. So right now we can see that we are at point A, and the value of theta is 30 degrees. So at point A, theta is something 30 degrees. But if we were to go to point B, which is right here, we actually would not be able to reach it if we just had this. We definitely would have missed. So we actually have to reduce theta by some amount. And only after reducing it by some amount could we reach the point. In fact, a little bit more reduction would be needed. And we can actually see that the angle now is something around 20 degrees. So we had to reduce the angle from 30 degrees to 20 degrees to reach this point. After which, to actually reach the next point over here, theta would have to increase yet again. It still has to increase some more, and there, now we actually reached it. And if we see, the angle now is like 112 degrees. So clearly we saw that theta is going to change, is going to start off at 30, go down, and then increase. Now that's how we've made theta to go. It starts off, goes down, and goes back. Of course, this is not to scale. It's just arbitrarily taken to show the points. But this is what the trajectory of theta would look like. If we were going if theta was increasing at a constant velocity. And this is a linear trajectory planning for theta. And this actually has quite a few problems, which we'll actually see over here. If we were to actually watch the animation, one thing that you can notice is the actual trajectory. If you see the trajectory, it's not a straight line. And that's why right now what we're doing is we're doing joint space trajectory. So we did the inverse kinematics for two joints, for 2 points, and we're just letting the robot go according to how it wants. And right now, this is happening linearly. Theta is always changing values at the same speed from this point to this point, and the same speed from this point to this point. There are two different speeds, but it's the same between these two areas. And you can see that there is a region of almost infinite acceleration, because right here, as it switches direction, there has to be an infinite acceleration for it to switch direction, which is not possible for a normal motor. It would also cause a high torque, and our robot might just topple over. So to fix that, we have different mechanisms. And those mechanisms are called the cubic spline. There are multiple. There's cubic spline, and we'll go into a few more after this. But the first one that we can talk about is called the cubic spline. And there we define theta not as a straight line. As you all know that if we were to determine theta over here, it would have been a straight line, which would have been in the form theta is equal to a0 plus a1t, right? Y is equal to mx plus c. And that is what would have been the equation for this. But the reason why we can't do that is that when we actually differentiate it to get what's called theta dot, which is the angular velocity. This right now, theta, is angular position, right? Over here, at any point of time, we have the angular position. we can find out what this position is. And this is what we are plotting. We are plotting that over here. What is the position, angular position with respect to time? We could as well plot theta dot, which would be the angular velocity. But for this course, we are not going to be plotting that. But that particular curve, would actually be just a constant. Because if you were to cover out this much, if you did not have these two terms and you had only the first two terms as it is in this case, it would just be theta is equal to a naught plus a1t. And if you differentiated it, you would have gotten the velocity, the angular velocity, and that would have simply been a1, which is a constant. So you would have to move at a constant velocity. You have no possible control over it. And if you did theta double dot, your acceleration would be 0. But when you change from this line, this curve, this line to this line, your velocity instantaneously goes from negative to positive, which would cause an infinite acceleration, and you don't have control over that. Which is why we write theta in terms of a cubic equation, where you could differentiate this and you would have 4 more constants, and with those constants you can actually control what the velocity should be at each point. And that would actually give you a curve something like this. If you see here, we could actually start off with almost 0 velocity, slowly increase our velocity, which is like the slope of this graph, then again slowly go back to having 0 velocity at B, and then slowly starting again and slowly ending with 0 velocity at C, which is velocity is the slope of this curve. Hopefully you can realize that. So that is the advantage of having a cubic spline. The trajectory of theta would look like this. And remember that we have inverse kinematics for A, B, and C. So we did inverse kinematics only 3 times, but we're figuring out the value of theta for every single point in between by using a simple equation, a cubic equation. And one more thing is that how are we going to get all of these theta values? Like, how are we controlling the motor to give out these values of theta? That is a whole different subject which comes into control systems. And our next course, the practical mathematics for robotic applications, will actually talk about how we get these values of theta, like how we actually make the motor reach these values. And that actually shows how complicated of a subject, how interdisciplinary robotics actually is. But anyways, apart from cubic spline, if we differentiated it twice to get the acceleration, we would have a straight line for acceleration. That means there would be no control over the acceleration, the same way how we had no control for the velocity in case of linear variation of theta. We had no control over velocity. Cubic splines, we'd have no control over our acceleration, which would mean we'd have an infinite jerk. Jerk is the rate of change of acceleration, and we'd have an infinite of that while we switch from one point to another. So we actually go into something called the quintic spline, where we can actually have an entire control over the acceleration as well. But again, for this course, we will not be going into too much detail about that. The next possible thing that we have is actually called parabolic blends. So right now, another problem is that even here, the user is who would have to decide what time it should take to go from here to here. Our computers, our robots would not be doing that. And if our robots were to do that, I mean, they could, but that would again become a bit computationally exhaustive. So we go into the next easiest thing, which is a parabola. So while changing directions, we all know that instead of having a cubic equation, we could have a simple quadratic equation, and the equation of a quadratic equation gives us something like a U-shaped curve, which we all know is a parabola. So parabolic blends goes like this. They have linear sections in between 2 points, but as we start approaching the point, we decide to shift from linear movement to a parabolic movement. So our motion changes into a parabolic motion, and then again becomes linear. And with a little bit of math, you could calculate what the ideal velocities should be and how much the time it should be from here to here, and before it starts a parabolic blend, how much of time it would take to undergo the parabolic blend, and this would be symmetrical, etc., etc. And then again, what should be the ideal time to start off the parabolic blend to have these changes. But here we actually see that we do not actually reach this point B. This is point B, as we're seeing, we're reaching it while we're going linearly. But in a parabolic blend, we don't actually reach the point. And that, yeah, in some situations you could say that's a bit of an issue. But for most pick and place robots, as we showed all the way in our first slide, for most pick and place robots, if an obstacle was to appear somewhere, it would be best if I showed it here. Suppose our obstacle was over here. We had an obstacle right here. Let's just add in an obstacle like a cube. We're not really hitting the obstacle, so we are avoiding it, and that's all that we needed. So that's why parabolic, whether it's a parabolic blend and we don't reach the desired point, it's all right. But in case we do want to reach that point, so let's say that we do want to reach point C no matter what, we put in pseudo points. So that would be like C dash and C double dash in these two areas, both of which we would not be able to reach. We'd actually miss, and that would change this linear curve a bit. So we'd actually have to maybe speed up a bit if we want to maintain the times. But yeah, this would be our linear section, and we'd have a parabolic blend here followed by a small linear section which would have C. That linear section would cross through C followed by another parabolic blend, which would look something like this. Just assume that this is a nice parabola, and so is this, and we have a little linear section over here which is touching C. That is what a parabolic blend would be, and that is how we would figure out the trajectory required for our robot. And that is actually all we have for trajectory planning in this course. Trajectory planning and things like that become a little bit more mathematical. It becomes very mathematical, in fact, and our next session will also be just as mathematical, if not more. In fact, actually, it would be a lot more mathematical. But the fifth session that we have, which is based on microcontrollers and things like that, the mathematics reduces a lot, and it would be much, much more interactive. So again, the session has officially ended, but there's still another 15 minutes left. As I said, this class will be 45 minutes. The next session will also be only 45 minutes. The session after that would also be at most 45 minutes. Does anyone have any questions from this session? Anyone who has any suggestions, feedbacks, questions, doubts related to anything, you can comment it on in the comment section. And we will go through it. Anyone? Anything? Okay, we have one question asking what method is used for robot commercial.xyz. Which, what? I'm not sure I understood the question. What method is used for robot commercial XYZ? I'm Oh, but both have much power. Compute computation. Marcelo Acevedo, I'm not sure I'm understanding your question. Can you rephrase the question in a different way so that I can understand it? For the animation that we did, for this animation, we actually had it at linear. The way we were moving this theta, the way we were going about was at linear, which in fact could be changed in case you guys want to see how it would look in a different way. Of course, one of them would be called Bezier. So if you see Bezier, it slows down as it's reaching. There's a nice slowing down that happens. So that is what would be the difference by changing these ways of theta, the value of theta, the speeds of thetas. Whereas linear, if you wanted to see the difference, is like this. This actually linearly slows down and doesn't. Constant is in between. So this is what a linear value would look like. Okay, if anyone has any other questions or feedback or anything of that sort, please do let us know through direct messages on Instagram or questions. You could even email us if that is what you guys want. Theta or XYZ? Yes, more used is always theta. Theta and L. That's called the joint space. So our joint space is what we generally use while uh, deciding trajectories for robots. We always tend to go depending on the joints that there are because that would cause lesser number of inverse kinematic equations to be solved. because inverse kinematic equations are not linear equations. They are trigonometric and other non-linear equations. And solving non-linear equations takes a lot more time for a robot. So we always tend to design everything with theta and L. So if you want to design an arm robot, it would have mostly revolute joints. Arm robots generally do not have prismatic joints, although you could have one prismatic joint as well. But depending on the number of joints, you could go through DH parameters to find the transformation matrix, or you could actually do that geometrically. For example, here, this particular arm is very simple to have a relation between the joint space, which is in this case just theta 1 and theta 2. With just theta 1 and theta 2, we could actually find out what the value of xy coordinates of this end effector is, simply because we know that the x coordinate is going to be theta 1 cos, it would be this link length. You have to know the link length, so it would be link length. We'll say that this is L1 and this is L2. In fact, I'll add it in. So if this is L1 and this right here we call L2, we know that this length from here to here would be L1 cos theta 1, and the length from here to here would be L2 cos theta 2, and that would give us the x value. So our x value is actually L1 cos theta 1 plus L2 cos theta 2, and our y value would simply be L1 sin theta 1 plus it would actually be, L1 sin theta 1 plus L2 sin theta 2. And with that, we could calculate what the relation between theta and x, and we could differentiate that to find out what the velocities, etc., would be. And in fact, that is one of the most used examples that you'll see on the internet if you do search for trajectory planning. And yes, you could use an Arduino with XYZ coordinates if it is for a very small amount. The thing is that, again, if you are using just XYZ coordinates, using your Arduino, you'd say you have to go to theta 1. Arduino has inbuilt functions to go to theta 1 and theta 2 and stuff like that using your servo motors. You could do that, but the actual path followed by the arm will be slightly erratic. It would be something like this. As you can see, the path is not a straight line. So using your Arduino, you would technically do exactly what we did right here. You would find out what the link lengths are, you'd find out what the x and y value is, then you'd find out what the necessary values of theta are to get what the values of theta will be to get to the next point, and you could simply put in those values of theta to the Arduino code, and the servo motors would output exactly that angle. But the actual final motion of the robot would be slightly erratic. Are there any other questions before we end this session? This session has another 4 minutes to go before we officially end it. Whoever is still watching this, I would suggest that you tell all of your friends as well who are interested in this course to watch this session as it is going on live rather than watching it later on. And because what's actually being monitored is the number of people watching it live, so we'd conduct more and more sessions, more and more courses, if we have more people actually attending them live rather than watching it afterwards. So do try to make sure that all of you watch the next few sessions live, and also tell everyone else to watch them live itself and not later on once the session has ended. All of these sessions will be there on YouTube on both the channels, PhysiFacts as well as IEEE RAS, but live is what we are focusing on, so we'd really appreciate it if everybody watched them live. So with that, if there's any other question, we'd like to address them for another 2 minutes, less than 2 minutes in fact. If there is nothing, then tell us that there's nothing and we can actually end the session now itself rather than waiting for another 2 minutes. The next 2 sessions will also be at most 45 minutes. The actual substance of the session will be for 15 minutes at most. It will be for 30 minutes to 35 minutes at most, and we will have questions for 10 to 15 minutes at the end. Okay, so since it looks like there are no other questions and no other doubts, 45 minutes was the time of the session, and it's almost been 45 minutes. So thank you all for joining this session. I would really like to see all of you join back in the next session and the next session after that. There's one course coming up again by PES University's RAS student chapter from IEEE, which is on practical mathematics for robotic applications.